Okay, this is section 5.6, part 2. Alright, Mr. Hoyle is falling from a ladder. So, for those of you that aren't aware, one time Mr. Hoyle, over Thanksgiving, fell off his ladder. Quite scary when he told me the story. And I do think he got hurt, but not fatally, obviously. So that's where this problem came from. Suppose Mr. Hoyle is on a 15-foot ladder that starts with a base 5 feet away from the wall. The ladder begins to slide away from the wall at a rate of 1.75 feet per second after 3 seconds. How fast is the tip of the ladder moving down the wall? What will hurt more, his pride or his arm? Which I think is ultimately what he hurt. But anyway, hopefully this situation, I can convince you, is a related rate situation. Let's draw the diagram here. So here's our wall. Here's our ladder. It's sliding down the wall. So the tip of the ladder is sliding down. So let's think at the outset here that our answer should be a negative value because it's moving downwards. We'll call this distance y. Again, just keeping in concert with the xy plane. And so we'll call that distance x. The length of the ladder, I can actually label that, right? This is 15. Unlike the police car situation from the other video, in this situation, the distance from here to here is not changing. It's constant, so it's 15. All right, so hopefully I can convince you this is a related rate situation because as the ladder moves down, the tip is going to be moving faster, let's say, down here than it is when it's way up here, even if this is moving at a constant rate away from the wall, okay? So that's step 1. Step 2, develop a model that relates everything in the picture. So how about the Pythagorean Theorem? X squared plus y squared equals 15 squared. Now, sometimes you might guess wrong with your model in your relationship, the way you've set it up, but eventually, and this will probably happen in step 5 when you go to try and solve it, eventually you'll hit a point where you'll realize that you don't have the information you need to solve the problem, and you can go back to the drawing board. Okay, so our model is the Pythagorean Theorem. Step 3, take the derivative. So this will be 2x dx dt plus 2y dy dt is equal to the derivative of 15 squared, which is 0. Okay. Now, if you had labeled this z, that's fine. At this point, when you went to take the derivative of your model for z squared, or maybe it would be at the next point, the next step, once you list everything out. But at some point, you're going to see that z will drop out because the rate of change is 0. Z is 15 and dz dt is 0. So anyway, step 4, write everything down that you know. X equals 10.25. Oh, wait. Well, hold on. We know dx dt. Dx dt is 1.75 feet per second. X, this distance we don't know, but we can figure out. Yes, we can figure that out. And I'll show you how in here in a second. Y, we don't know. And dy dt is what we want to know, right? Dy dt ultimately is what we want. We can figure out what x is because we know that it's going 1.75 feet per second for 3 seconds, and it starts off 5 feet away from the wall. So you're going to take 5 plus 3 times 1.75. So that distance ultimately is going to be 5 plus 3 times 1.75, which gives you a distance of 10.25. So if you know that this side is 10.25, you know that this length is 15, you can figure out what y is. Y turns out to be the square root of 119.375 when you use the Pythagorean Theorem there. Okay, if you lost track of what was going on there, maybe rewatch that part, or definitely feel free to ask me questions in class about how I got those values. Now we're going to plug everything in. So I've got, again, the 2's are going to drop out here, right? If I divide everything by 2, I don't need the 2's. So I'm going to have 10.25 times 1.75. That's x dx dt. X times dx dt. Plus square root of 119.375 times dy dt equals 0. Solve that for dy dt, and you end up with this. Dy dt is equal to negative 1.63 feet per second. Okay, and so that was actually step 6, right? So that's how you do that one. Let's go on to the last question, which is the conical tank problem. This is just a classic calculus problem. And it's a little bit more involved than the ones that we've done up until now. So water runs into a conical tank at a rate of 9 cubic feet per minute. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? So let's sketch this out. We have a conical tank. The tank, the height and the radius of it is not changing. So the height is 10, so we can label that. The water, well, actually, hold on, let's label the radius. So the radius is here. It's going to be 5. So that length is 5. And then the water is somewhere in here. Water's pouring into this tank, and so the radius of the water is unknown and it's changing. And then the height of the water is also unknown and it's changing. So we'll label that R and H. And then so for step 2, we need a model that's going to relate V, the volume of the water, R and H. And so that's just going to be the volume of a cone. So it's going to be V equals 1/3 pi R squared H. All right. Now, we can go from here and we can develop a model for the derivative. Like we can take the derivative and use the product rule here. Fortunately, we're going to run into an issue where we've got too many variables. So I'm going to show you how to approach this and how to make the problem simpler at the beginning. So to solve this problem, I'm going to notice that I've actually got similar triangles here. So I can use the fact that this triangle of the water and the triangle of the tank, those two triangles are similar. And then I can eliminate one of the variables from my equation here. So I don't have to use the product rule ultimately, right? So let me show you how to do that. I'm going to sketch these triangles out here on their own. So this is the tank triangle. I know that this is 5 and this is 10. Actually, I'm not going to label that there. I'm going to label it here. So the height here is 10. And then here is the triangle in the water, so that's R, and this distance here is H. And so I can set up a relationship between the sides of the triangle. So maybe I say that like R is to H as 5 is to 10, or actually I guess I did vice versa in my, no, I want that actually. So R is to H as 5 is to 10. Okay, and then I can solve this for R and eliminate one of the variables over here. I don't think it actually matters which one you eliminate, except for the question is asking how fast is the water level rising. So that's asking how fast is H changing. So it's asking for dHdt. So we wouldn't want to eliminate H from our equation. We would want to eliminate R so that we leave H in the equation. So if I times both sides by H over here, I get R is equal to, this is 1/2, so H over 2. So I'm going to take this, H over 2, plug it in for R, and we're going to simplify. So I get V equals 1/3 pi R squared, so that's H over 2 squared, times H. When I clean this up, I end up with my formula for volume as 1/3 pi, no, I'm sorry, that's not right. Once you clean it all up, you're going to get H times pi. So pi H cubed over 12. Okay, so that's much simpler. All right, then step 3, I'm going to take the derivative. So I'll get dv dt is equal to, this will ultimately be 3, losing track of my spot, 3 pi H squared over 12 times dH dt. Okay, so I've taken the derivative. Now step 4, write down everything that I know. So I know that dv dt, that's given. dv dt is 9 cubic feet per minute, so 9. I I know that h is 6 feet because I want to know when the height of the water is 6 feet, how fast the water, I'm sorry. Yes, no, that's right. I want to know when the height is 6, how fast it's raising. And then dh dt is what I ultimately want. Okay. I'm just going to drop everything else in and solve. So step 5, I got 9 equals 3 pi times 6 squared, because r is 6, divided by 12, times dh dt. And then I'm going to solve this out. Now, yes, you could right here, 3 over 12 ends up being just 1/4, so you could simplify that even further at step 3. All right, so then once you solve this out, for step 6, you end up with dh dt equals 0.318, and that is feet per minute. Okay. Again, units are important here. Make sure that you get the units, you pay attention to the units, that will matter on the quiz. And then also make sure that you should also double check to make sure that you can do the math to get out to this number. And I'm trying to think if there's anything else I wanted to say about this problem. Oh, if you had started off and you had not eliminated r, you would have had to come to similar triangles eventually, because you would have had r and h in your derivative, and ultimately you would have had too many variables at step 5. So you would have had to go to similar triangles to eliminate those variables anyway. Your equation also would be much more complicated at this point. So it's definitely better to eliminate earlier on if you remember to do so. I think that finally wraps up related rates in section 6 as far as the direct instruction goes.